Hello and welcome to this chemistry lecture series. In this video, we're going to look at chapter 12, section 2, and now we're going to move into the reactions of the group 17 elements, the halogen reactions. We looked at the physical properties in section 1. Now we're going to move on to their chemical ones. So halogen reactivity, before we talk about the individual reactions, like the reactions with hydrogen, for example, let's talk about how reactive the halogens are. When halogens react, they're going to do one of two things. If they're reacting with a metal, they're going to gain one electron to form a -1 anion, like we discussed in section 1. When they undergo this reaction, because they're gaining an electron, this is technically a reduction reaction. For example, when chlorine reacts with something like sodium, a metal, it forms sodium chloride. In this process, the chlorine, or any halogen when this happens, is going to be reduced. The Cl2 molecule is going to gain 2 electrons, one for each atom, creating 2 chloride ions, Cl-. We see this here as a overall reaction, but in reality, remember that this sodium chloride, this ionic compound here, is made out of 2 ions. And this is something that's very important. We often forget about whenever we are talking about reactions. We forget to look at the individual compounds. This compound right here, this sodium chloride, is made out of a sodium ion and a chloride ion that are being attracted to each other through electromagnetic forces. All right, so do keep that in mind whenever we are looking at these molecules, or these compounds, should I say. So that's what happens when a halogen reacts with a metal. When a halogen reacts with a non-metal, however, they're going to share electrons because covalent bonding is going to happen, and they're going to form a single bond with other non-metals. Now, some halogens like chlorine, bromine, and iodine can form expanded octets, but it is not very common and usually only happens in polyatomic ions. With iodine, chlorine, bromine, and fluorine, though, more commonly, they're only going to form a single bond to other elements. For example, if iodine reacts with hydrogen gas, when that reaction happens, the iodine is going to form a single bond with the hydrogen gas to create the hydrogen iodine. Just to show you the Lewis structures of these, when iodine, which is a diatomic molecule, so it's I bonded to I with lone pairs of electrons on each side. So with iodine and hydrogen react, the diatomic iodine reacts with a diatomic hydrogen to form hydrogen iodide. In that process, hydrogen and iodine form a single bond with each other, and the iodine still will have those lone pairs, in order to react. This is usually what happens with halogens when they form covalent bonding. They form only single bonds. It is very rare, very, very rare for a halogen to have a double or a triple bond, and that is going to require expanded octets usually. So we don't really see that on the AICE exam. Now, let's talk about how reactive these halogens are, because in both of these cases, when the halogen is being reduced by a metal, like in the case of chlorine becoming the chloride ion between the reaction of sodium, or whenever they are forming a covalent bond, this requires the halogens to attract electrons towards themselves, meaning that we're going to be talking about the electronegativity of the halogens when we're talking about their reactions. So the electronegativity becomes very important. So what is the trend in electronegativity for the halogens? As we go down the group from fluorine to chlorine to bromine, iodine, and astatine, the electronegativity of those elements goes down. Now you should know this. We've studied this already. We looked at not just the periodic trend of the electronegativity decreasing down the group, but we also looked at why in earlier chapters. As we go down the halogens, the size of the atom increases because we get more and more energy levels. Fluorine only has two energy levels, energy level 1 and 2 in its electron configuration, whereas astatine has 1, 2, 3, 4, 5, 6, actually 7, 1, 2, 3, 4, 5, 6, sorry, 6 energy levels into electron configuration. So because we have more and more energy levels in the atom, they get larger. So the size of the atoms increase. So does their shielding. And remember, shielding is that repulsion felt by the valence electrons from the inner electrons. So because these outer electrons, as we go down the group, are more shielded and they're farther away from the nucleus, they're easier to remove. So that increases their ionization energy, and for the same reasons, their electronegativity. If an electron is out here, this iodine is going to have a much harder time attracting that electron than fluorine will. So for example, let me draw up an electron here. If I had an electron out here that the iodine is trying to attract, that it does not belong to it, versus fluorine, the fluorine is going to be much closer, the nucleus on the fluorine, which is the positive element, or positive part of the element, is only much closer to that outer electron that does not belong to fluorine than it is in iodine. It is much farther away in iodine and has to go through more shielding. And so as we go down the group, the electronegativity is going to decrease. It makes it much harder for those nuclei in the halogen to attract the electrons that don't belong to it, meaning that its electronegativity goes down. Fluorine is the most electronegative element out of all of the halogens, and in reality is the most electronegative element, period. And it attracts electrons more strongly during chemical reactions. Well, if it attracts electrons more strongly, that means that fluorine is the most reactive element out of all of the halogens. The electronegativity and the reactivity of halogens are tied together. As we go down the group, they get less electronegative, meaning they also get less reactive. So let me put an arrow for that here. We don't have one. But as we go down the group, not only does the size increase, the shielding increase, and the electronegativity decrease, but also as we go down that group, the reactivity decreases. The reactivity of those halogens is going to decrease on the group because the electronegativity decreases and they're tied together because they're always attracting electrons when they react. So let's keep moving forward here. Let's talk about a specific kind of reaction that happens with halogens. Halogens can actually react with each other, but they do so in what we call displacement reactions, which we learned in honors chemistry as single replacement reactions. Here, the chlorine, Cl2, is reacting with sodium bromide. Whenever we have these type of reactions, we're going to have a diatomic halogen replacing a ion halogen, or halide, should we say, because it is the ion. Meaning that we're going to have something like X2, and we'll just put X2 to symbolize one of the halogens, replacing X minus here. So we can see that in these reactions. These are called displacement reactions. They displace the ionic form of the element. A more reactive halogen like chlorine can displace the bromide ion in a compound because it is more reactive than the bromine. So in this case, the chlorine replaces the bromine in the sodium bromide because it is a single replacement reaction, and the bromine leaves. So the bromine becomes Br2, which is a liquid, as we saw in section 1, plus sodium chloride, because the chlorine becomes the chloride ion. Now, these reactions, being single replacement reactions, do not always happen. Remember that in honors chemistry, we learned about the activity series. And there was a specific activity series for nonmetals that only included the halogens. This is why. Halogens are only going to be able to replace each other if they're more reactive. A more reactive halogen, in yellow here, will have to replace a less reactive halogen in a compound. The more reactive halogen acts like an oxidizing agent. It oxidizes the ion of the halide, and the halogen diatomic molecule gets reduced into the ion. So again, the oxidizing agent is the more reactive halogen. So in this case, the chlorine is the oxidizing agent. Actually, let me use the colors that we have here. I'm gonna get rid of all these arrows. So the chlorine is going to be the oxidizing agent, meaning it gets reduced, because remember, word agent means that it's undergoing the opposite. Whereas the bromine, which is getting replaced, is going to be the reducing agent, meaning it is getting oxidized. And so that's what we see here. The oxidation numbers of this in sodium bromide for bromine is -1, but the bromine here is 0, meaning that its oxidation number is going up, it's getting oxidized. Whereas for the chlorine is going from 0, because it's just bonded to itself, to be -1 on the sodium chloride in the products. Like I said, this does not always happen though. Just like we learned with the activity series earlier in honors chemistry, as we go down the groups, the halogens get less reactive going down the group. We just talked about the electronegativity. Well, because they get less reactive, and because a more reactive halogen has to displace a less reactive one, halogens can only replace those below them. So fluorine can replace any compound, meaning that F2 can replace chlorine, bromine, or iodine in an ionic compound. However, chlorine, which is the second most reactive halogen, can only replace bromine and iodine in a compound, but not fluorine. So we can see here that chlorine is able to replace bromine only because chlorine is higher than bromine on the group. But it wouldn't be able to replace fluorine if this was NaF, there would be no reaction. Bromine can only replace iodine because it's only more reactive than iodine, but it cannot replace chlorine or fluorine. And then iodine can actually not replace any other halogen. So if we can see here, I2, solid, if it were to be reacted with sodium bromide, aqueous, there will be no reaction because iodine is less reactive than bromine. It is lower in the group, has a lower electronegativity, and therefore cannot oxidize the bromine. So this is important to know, and this is actually a very common thing that comes up on the AICE exam to see whether you can not just figure out whether two halogens will replace each other, but if you can explain why. Let's keep going here. Now, the identification of the halogens in the solution. Once we do this reaction, so we're still talking about this type of displacement reaction, which in its products is going to have, whether it happens or not, an aqueous ionic compound of with a halide ion and a diatomic halogen, whether it happens or not. If it doesn't happen or reaction happens, we still have iodine, we still have sodium bromide aqueous. So the color of the solution of the displacement reaction actually comes from the diatomic molecules. These aqueous solutions are somewhat colored. We can see here chlorine is a bit light, but it's a very pale white color or pale clear color. Bromine has this like brownish yellowish color, and then iodine actually has a very tinge of yellow, but you can see it here. It's so faint, even in the picture you can see it. So these are the aqueous solutions. Really hard to tell them apart. Even with bromine, it could be confused for iodine because it's also pale yellow. So these solutions, the color of the halogens in solution, aqueous solution, are not very easily distinguished. The color is so big, it's so faint that does not provide a conclusive molecule or a conclusive test for whether the molecule is present. So if I just saw this, I couldn't tell you whether this was chlorine or iodine. Or even with bromine, I couldn't tell you that was bromine or iodine clearly because the colors are so faint and so similar to each other. However, there is one way to tell which diatomic, not ion, which diatomic molecule is present in an aqueous solution of iodine. Halogens are, because they're extremely non-polar, and that is very important here, are going to be very soluble in cyclohexane. Now, cyclohexane is something that we will talk a lot more about once we get into organic chemistry, but cyclohexane is also non-polar like the halogens, meaning that cyclohexane and the halogens are very soluble in each other. The halogens will easily dissolve in cyclohexane because, as we already studied, remember, like dissolves like, similar compounds will dissolve each other. And because both the halogens and the cyclohexane are nonpolar, they'll dissolve in each other. However, water is not polar. Water is very polar. Water is not going to mix with cyclohexane, and we say that water and cyclohexane are immiscible. So we say that water and cyclohexane are immiscible, which is a word that means that the liquids just simply do not mix with each other, kind of like oil and vinegar are immiscible. When we put a amount of cyclohexane in an aqueous solution of water, they'll separate, like we see here. They will not mix with each other. So what can we do? If we have an aqueous solution and we want to know which diatomic molecule of the halogen is in that solution, we can run this particular test. So again, we're looking for the diatomic molecule of the hydrogen because that's what gives these solutions their color. So what can we do? We add a little cyclohexane on top of the aqueous solution of the mixture. And again, if we are doing the displacement reactions, we can see which diatomic molecule is there. And then we're going to shake this. And just like oil and vinegar, when you shake it, they'll mix and then they'll separate again. And what happens is that because the halogens are so soluble in the cyclohexane, the halogen molecules, in this case the Cl2 for the first one, the Cl2 here, the Br2 here, and the I2 here are going to instead be dissolved into the cyclohexane. A little bit of the halogen still stays dissolved in the water, but a lot of it goes and dissolves in the cyclohexane. And the thing about halogens and cyclohexane, they have really, really clear and amazing colors. When chlorine dissolves in cyclohexane, we see this pale green color right here that we can use to identify the chlorine. When we get bromine in cyclohexane, we see this really deep, rich orange color. And iodine is the most clear. Iodine in cyclohexane gives this bright purple color. So what happens? If we have a solution, an aqueous solution, for example, if we were looking at these molecule or these reactions that we saw earlier, and we add chlorine to sodium bromide, and we wanted to see whether the bromine got made or not, or whether we still have chlorine, we'll undergo this reaction in water. We'll then add cyclohexane to that, mix it, and let it separate again. And depending on the color of the cyclohexane, if it's pale green, we know the reaction didn't happen because we still have chlorine in there. But if it's orange, then we know the reaction did happen because we have bromine in that solution. So this is a very useful way of identifying halogens. Or even if you have an unknown sample for aqueous solutions of halogens, you wanted to know which one it is, you can just add cyclohexane, mix it, let it separate again, and then look at the color of those cyclohexane layers at the top. Now, be careful. Fluorine does not do this. So we cannot do this with fluorine. Fluorine is more dangerous to work with because it's so reactive. So we will not be able to run this test with fluorine. So that's one reaction. That's the displacement reaction of the halogens with each other, essentially, between the ionic and diatomic forms of the halogens. Let's look at the reaction of halogens with something else. Let's look at the reaction of the halogens with hydrogen gas specifically. Because this is a very common reaction, very telltale reaction of chemistry. And it tells us a lot about how the halogens react and how they form molecules. Halogens combine with hydrogen gas to form what we call hydrogen halides. For example, hydrogen chloride or hydrogen bromide. Hydrogen halides are just going to be HX, whereas X is a halogen. So hydrogen, a 1-to-1 ratio between hydrogen and a halogen. Hydrogen chloride, which is HCl, is a hydrogen halide. Hydrogen bromide, HBr. Hydrogen fluoride, HF. Hydrogen iodine, HI. Now you might be asking, Mr. Pendola, why are we calling these hydrogen halides, right, like hydrogen chloride, when we know HCl as hydrochloric acid or HBr as hydrobromic acid? Well, one very important thing to distinguish here is the distinction between hydrogen halides and acids. And it's actually a very, very small and silly distinction here that we're going to look at. But the difference between when HCl is called hydrogen chloride versus when HCl is called hydrochloric acid is its state of matter. And this is true of all of these. When HCl is a gas, which is its common state of matter, that is a hydrogen halide. Acids, by definition, are going to release hydrogen ions in water solutions, meaning that HCl aqueous is hydrochloric acid. So what we study as acids, we got to be careful because they're only acids when they're aqueous. If they're not aqueous, and even sometimes when they're aqueous, depending on the context, they're called hydrogen halides. So the molecule, the compound is the same thing, HCl. It's just whether we call it by its acid name or its essentially ionic name, hydrogen halide, is whether we have a gas or an aqueous solution. So be just cognizant of that. Just know that if someone says hydrogen chloride instead of hydrochloric acid, it's most likely because it's in the gaseous state of matter and not in an aqueous solution. And we're probably talking about a reaction like this one. So I digress. So what are hydrogen halides? We just talked about that. How are they made? Hydrogen halides are made when hydrogen gas, H2 gas, is combined with a halogen. In the case of fluorine and chlorine, that will be fluorine and chlorine gas. Because bromine will be liquid, iodine will be a solid in its natural state of matter. But most of these reactions happen with the gaseous version of those elements. So we can see here the reaction for every single one of the halogens. We have H2 gas reacting with either F2, Cl2, Br2, or I2 in the gas state. So for bromine and iodine, we have vaporized, or we have evaporated these compounds, or these three elements, into the gas form before the reaction happens. When this reaction happens, the hydrogen and the halogen atoms are going to form a single covalent bond and create the hydrogen halide, hydrogen fluoride, hydrogen chloride, hydrogen bromide, or hydrogen iodine. Now, these are single covalently bonded compounds, and we'll see that in the next slide, but they're all going to look like this. H with a single bond to the halogen, and that halogen will have three lone pairs of electrons to form that octet. So this is always going to be the case. The reaction happens with every single one of the halogens, but it is, as we go down the group, less reactive or less explosive, I guess, is a way to say it. As we go down the group, we already looked at how the reactivity of the halogens decreases because their electron activity decreases. Well, as we go from the reaction with hydrogen and fluorine to the reaction of hydrogen with iodide, they become less volatile or less explosive. with hydrogen and fluorine, the reaction is explosive. Even if you do this reaction in a cool, dark place, the reaction is going to be explosive between hydrogen and fluorine, which is why this reaction is usually not carried out because it is dangerous. With hydrogen and chlorine, the reaction is explosive in sunlight. So if you do this reaction with hydrogen and chlorine in the dark, in a cool, dark place, the reaction doesn't explode. But if you do it in sunlight, it explodes. Why? Because chlorine is still very reactive, just not as reactive as fluorine. Once we get to bromine, that's when the reactions become more manageable. The reaction between hydrogen and bromine gas is more slow, and it has heating as a condition that needs to for the reaction to happen. So this reaction does require heating. It requires a source of energy, and it will happen slowly. So this shows you that bromine is less reactive than chlorine and fluorine because the reaction is not as volatile. And finally, with iodine, the reaction needs heating as well, like it did with fluorine, but the iodine is so much more less reactive than any of the other halogens that the reaction forms as an equilibrium, not as a full reaction. So we get an equilibrium reaction. When we react hydrogen and iodine, we get a mixture of the hydrogen iodide and the hydrogen and iodine molecules in the reaction vessel. The reaction never goes all the way to completion. And that's again because of the reactivity of the halogens and how that decreases as we go down the group. Now, if we keep going here, now let's talk about why this happens. And again, we kind of went over why in past sections or in past slides, but we're going to recap a little. Hydrogen halides, the reaction themselves and how extreme the reactions are, have to deal with the reactivity of the halogen. But they also have to deal with the stability of the halide. The more stable a hydrogen halide is, the more the reaction will be explosive or be volatile, because it's creating a much more stable compound from much more unstable ones. So let's talk about the thermal stability of the hydrogen halides. Hydrogen halides become less thermally stable going down the group. Now, what is thermal stability? Thermal stability is the ability of a chemical to resist decomposition when exposed to heat. What does that mean? That means how quickly it decomposes when it's heated. So the more thermally stable something is, the higher the temperature needs to be for it to start decomposing and breaking apart. The lower the thermal stability of something is, the more quickly at a lower temperature it will start to break apart. The decomposition is exactly the opposite of these reactions, right? Because if we have hydrogen fluoride and we heat it up and we decompose it, it turns into hydrogen and fluorine. If we have hydrogen iodide and we decompose it with heat, thermal decomposition, it breaks up into hydrogen and iodine. So what does that tell us? What happens here? As we go down the group, fluorine, chlorine, bromine, and iodine, hydrogen halides become less stable, meaning that it takes a much higher energy, a much higher amount of energy for hydrogen fluoride to start breaking apart into hydrogen and fluorine than it does for hydrogen iodide. Hydrogen iodide will start turning back into hydrogen and fluorine at a much lower temperature, and we saw that that's why it's an equilibrium reaction, than hydrogen fluoride. As we go down the group, as we said before, the halogens get larger. The atoms of the halogens get larger. Well, as those atoms get larger, that is going to change the bond length. Remember that the bond length of a compound is written down as the distance between the nuclei. So if we have two atoms that are bonded together, the bond length is the distance from one nucleus to the other. Well, if we have one of the atoms always be the same, which is always hydrogen, but the other atom is a halogen that, as we go down the group, gets larger and larger and larger, the bond length is going to increase as we go down that group, because that atom is larger and larger and larger. So we can see it more clearly here. As we move from fluorine to chlorine to bromine to iodine, which are larger and larger and larger in size, the bond length gets larger and larger and larger. Longer bonds, because the overlap between the the orbitals is smaller, are gonna be weaker and require less energy to break. As we go from fluorine to iodine, as the bonds get longer, their bond energy gets smaller. So the bond energy for hydrogen and fluorine is 562 kilojoules per mole because it is much smaller than the one for iodine, which has a lower bond energy of 299 kilojoules per mole. Meaning that the hydrogen-iodine bond is going to be a lot easier to break and requires less energy to break than hydrogen-fluoride bonds, and therefore it is easier to decompose hydrogen-iodine than it is to decompose hydrogen-fluoride. So hydrogen iodine is less thermally stable than hydrogen fluoride for this reason. So make sure that you remember that, because you will need to be able to explain this. Explain not just the trend in thermal stability of the hydrogen halides, that they get less thermally stable as we go down the group, but also why. As we go down the group, the atom of the halogen gets larger, which makes the bond length longer. Longer bond length means lower bond energy, and so it's a lot easier to break that bond and decompose a compound. That's it. That's the thermal stability of hydrogen halides, why it happens, and again, how that relates to the reactions between hydrogen and hydrogen. Why? Because remember, the decomposition of these is going to be the reverse reaction. So if something is very thermally unstable, like hydrogen iodide, or not very thermally stable, it's a lot easier to bring back into the halogens, meaning that that reaction is going to be a lot more back and forth. Whereas something is very thermally stable, like hydrogen fluoride, it's a lot harder to make this reaction go backwards, so the reaction happens more explosively. The difference in energy between, or stability, between H2 and F2 versus HF is going to be a lot larger, and so the reaction becomes more explosive. But yeah, that's it for section 2 of chapter 12. I will see you all in the next video to start going over some other very specific reactions of the halogens.